Hello everybody, it's your friendly organic professor back again for another installment of learning organic chemistry. So today we're going to talk about a structural determination, or at least we're going to begin to talk about it. We won't completely finish, but that's okay. The main thing I'm going to talk to you today is sort of a preview of class next week when we're going to go over IR spectroscopy or infrared spectroscopy. And so I'm also going to start by talking about mass spec and elemental analysis, or at least what you need to know about it for Org 1. So as sort of a lead into this, suppose I gave you a bottle of a chemical and it was labeled unknown 100. Tell me what's in it. What do you need to do? So you don't have much information other than, I guess, is it a clear liquid? And so where do you go from there? Well, the first thing to go to is this question. What's the molecular formula? How many carbons are in there? How many hydrogens? Are there oxygens? Are there nitrogens? Is there sulfur or something else? And there are two tools that we use to figure out what's the molecular formula. The first one is mass spectrometry. And I'm not going to go over really any of the details of mass spec. I could fill an entire course about mass spec, I think, if I really wanted to, and some people do. Suffice to say, it's an instrument that bombards molecules with electrons and then causes them to take on a charge and then measures the mass to charge ratio. Ultimately, from all that information, you can get out the molecular formula. In this case, I'm giving you something that has a molecular formula, molecular weight of 72.11. So, you know what, I didn't put units on that. Let me go ahead and do this here. So we'll call that 72.11, and it's a molecular weight, so grams per mole. The other thing, so that, that's helpful. All right, it's 70. It's got to be reasonably small. You can sort of put an upper limit on the number of carbons that could possibly be in this thing. Just because, okay, well, carbon has a atomic mass of 12. How many times does 12 go into 72? The next thing is like I said, is there oxygen? Is there nitrogen? Is there presumably there's hydrogen? What is there? So what we can do is use a machine called the elemental analyzer, and it will tell us how much carbon, how much hydrogen, how much oxygen, how much nitrogen. Some of them can do other elements as well. In this case, suppose we did an elemental analysis on unknown 100, and we got out this data. We got out that it was about 2/3 carbon by mass, 11% hydrogen, 22% oxygen. What do we do from there? Well, between the molecular weight and the elemental analyzer data, we can actually figure out the molecular formula. And all it is some dimensional analysis, good old dimensional analysis. So what we do is this. Let's start with carbon. We are organic chemists after all. And okay, well, we know that the molecular weight of this compound is 72.11. So we'll say 72. Oops. 0.11 grams per mole. Here, let's just draw a big old dimensional analysis line. All right, 72.11 grams per mole. We also know from the elemental analyzer that this molecule is 66.63% carbon. So if, for example, we had 100 grams of the molecule. Of that, 66.63 grams would be carbon. And then the last thing to do is say, okay, well, we know the atomic mass of carbon. So we know that for every 1 mole of carbon, that's, well, 12.01 grams of carbon. And, well, really, that's all the space I need. I can erase some of this here. And you can plug that into your calculator and figure out that you have, you get 4 moles of carbon, 4.0 moles of carbon per molecule, or rather per mole of unknown. I guess I didn't write, technically I should, if I want to put my units here, it's grams of unknown per mole of unknown. Let's do hydrogen next. Again, we start from the mass spec. We know we have 72.11 grams of unknown per mole of unknown. Now we know we have 11.18 grams of hydrogen per 100 grams of whatever this is. I guess I should call that unknown. And we have 1 mole of hydrogen per, check the periodic table, 1.01 grams of hydrogen. Plug that all out, and you get 8 moles of H per mole of unknown. Lastly, oxygen. Pause this and do it yourself if you like. Again, start from the molecular weight, draw your line here. 22.19% oxygen. 22.19 grams of oxygen per 100 grams of the unknown molecule. 1 oxygen atom per 16.00 grams. And you get 1.0 moles of oxygen per mole of unknown. Congratulations, we have figured out the molecular formula. So unknown 100 must have a molecular formula of C4H8. Oh. All right. So, now we can rule out some things. It's only got 1 oxygen, so it can't be an ester. It can't be a carboxylic acid. Well, it could still be a ketone or an aldehyde or an alcohol. So the next question to ask are, okay, what functional groups are present in the molecule? So we've talked about functional groups in the context of resonance. Now we're going to talk about them in the context of molecular structure and sort of how that causes the molecule to interact with light. So we chemists like to hit organic molecules with all sorts of different types of electromagnetic radiation. I won't talk about this whole slide today. Today, though, what we're going to talk about is, this week, about the interaction of organic molecules with infrared light. And that causes them to vibrate. So what we can do, take our unknown 100, our C4H8O, put it on an infrared spectrometer, and get out an IR spectrum, which in this case looks like that. Whoa, what is that? Well, we'll practice with these. Like I think I've said in class, you know, I like organic chemistry, or one of the things I like about organic chemistry, because there are all these puzzles. And to me, an IR spectrum is like a puzzle, or it's like a part of a puzzle, and that, you know, there are these rules that you have to follow, but you can get out all this information and start building your structure. So what I want to show you right now is, okay, these little dips here are called peaks. They look like valleys, but they look like what we call them peaks. The reason for that is on the y-axis here you see percent transmittance, so from 100 to 0. So if the molecule doesn't absorb a certain amount of energy of IR light, it basically gives this flat line at top. But if it has a functional group that does absorb IR light at a certain frequency, then you get a peak. It absorbs the light, and therefore it doesn't transmit the light. So you know, you get transmittance, you know, anywhere from 70–80% for the smaller peaks down to almost 0% for these larger peaks. The x-axis on this spectrum is in a unit called wave numbers, and you can't see it on this picture here, but what a wave number is an inverse centimeter. So 1/centimeter, or you'll more often see it written centimeter to the -1. And the reason that we use this funny inverse centimeter is, well, twofold. One is so that this way the x-axis is proportional to energy. So recall this equation, E equals hc over lambda. Lambda is wavelength. Wavelength can be expressed in centimeters, but if we use inverse centimeters, it's below the denominator, and so now this is proportional to energy, since h is constant, c is constant. The other reason centimeters just works out so that we can have, you know, this from 500 to 4,000, and I guess somebody decided that was a good way to talk about this. So every functional group has its own sort of signatures of what wavelengths it corresponds to. So tomorrow in class, I'll be giving out this sheet on a handout, but this is not something you need to memorize. You can put this on a note card for the exam, but it's a good thing to, you know, start learning some of these. We'll talk about the important ones in class tomorrow. I'm not going to solve unknown 100 for you on this movie, but you are welcome to try to use this table and the information before to work it out for yourself. If not, we'll finish this in class on Monday of next week. So see you then.